6. So let E contained in R. We say that it has an infinite condensation point if E has uncountably many points outside every finite interval. So you take any interval, outside that interval E must have uncountably many points. So and this should be true for every finite interval. Then you say E has an infinite condensation point. Obviously such sets are uncountable. So now let H be equal to P of R, power set of R, and you define mu star of E. This is 0 if E is empty, finite or countable. One if E is uncountable but does not have an infinite condensation point. Example is a finite interval itself, because the finite interval outside it doesn't have any points. So in particular finite intervals have measured 1 in this and plus infinity if E has an infinite condensation point. For example, whole of R will have, or R minus any countable set will have an infinite condensation point. Okay, so you have this thing. So 1, show that mu star is a sigma finite outer measure. On H. 2, only mu star measurable sets are countable sets and their complement. 3, mu bar is not sigma finite. So you are taking a outer measure on the power set, and these are the only mu star measurable sets, and you know that you have an outer measure and mu star measurable sets. The mu star becomes a measure on that set, and that measure we want to show is not sigma finite. Okay. So this is contrast to what we did earlier. We started with a ring which is sigma finite and went through the Carotheriot reconstruction. That if the ring were sigma finite, everything is sigma finite. Here we directly have an outer measure on the sigma ring, and it doesn't mean necessarily, even if it is sigma finite, it doesn't mean that mu bar will be sigma finite. Okay, solution. So 1, mu star is greater or equal to 0, obvious, and mu star of phi empty set is also 0, because that is how we have defined it. Now monotonicity. So E is contained in F. So if mu star E equal to 0 or mu star of E equal to plus infinity, nothing to prove, because automatically mu star of f will be greater than or equal to 0 and mu star of f will be plus infinity if mu star of E is plus infinity, because mu star of E is plus infinity means it has an infinite condensation point, and any bigger set will obviously have an infinite condensation point, and therefore there is nothing to prove. So now we have to assume, so let mu star of E be equal to 1. Okay, then so this implies E is uncountable. This implies that f is also uncountable. So if mu star of f is infinity, nothing to prove. So assume mu star of f equal to 1. But then again there's nothing to prove. Okay, so sorry, we don't need any argument. Implies mu star of f equals plus 1 or plus infinity. So again this implies mu star of E is less than or equal to mu star of f. So here obviously we have monotonsity also. So now we have countable subadditivity. So let us take E contained in union EI, I equals 1 to infinity. So again mu star of E equal to 0, nothing to prove, because we want to show mu star of E less than or equal to sigma mu star of EI. So this is what we want to show. So 2, if mu star of E equals 1, implies E is uncountable, implies there exists at least one I such that EI is uncountable. Because we have all the EIs are countable at most, then countable union of sets is countable, and therefore that cannot contain an uncountable set. And therefore this implies that sigma mu star of EJ is greater than or equal to mu star of EI, which is equal to 1, which is equal to mu star of E. So again we have countable subadditivity. Suppose mu star of E equals plus infinity. So this implies that E is uncountable. In particular, it means much more, and so we have to look at various possibilities. Sigma mu star of EI equal to 0, not possible, because all the EIs mu star EI will be 0. That means all the EIs are at most countable, and therefore the union will be countable, which is not possible because it contains an uncountable set. And then sigma mu star of EI is finite. That means, okay, this means mu star of EI is either 0, 1 or infinity. That means at only finitely many EI are uncountable and rest are at most countable. And these EI have no infinite condensation point. So let us assume, without loss of generality, we renumber them: E1 to En uncountable without inf condensation point, and Ej j greater or equal to n is all countable. So if I is any finite interval, I complement intersection Ej countable, at most countable, for all 1 less than equal to j less than equal to n, and in fact also for all j bigger than n. Okay, so this means that I complement intersection E is at most countable. Sorry, no, that's not the correct solution. So there exists Ij, finite interval, such that Ij intersection En is countable for at most. So now you take union j equals 1 to n Ij, okay, and then take the I equals largest or smallest interval containing union Ij j equals 1 to n. Okay, so then so this will imply that I complement into the, so this implies this. I complement intersection Ej is at most countable, and it's also true for all j bigger than n, and therefore you have this. Fine, because I is bigger than each Ij, so Ij complement Ej okay, so this implies that I complement intersection Ej at most countable for every j. Okay, and this means not possible again. Since mu star of E is plus infinity, it has an infinite condensation point, and therefore this is not possible. Okay, so this implies that mu star of E, sigma mu star of Ei equals plus infinity, and that proves the subadditivity. So this means that mu star is an outer measure. So second part, we want to show that S equals set of all E contained in R, E countable or E complement countable. So we want to show that these are the only mu star measurable sets. So if E belongs to S, okay, then and A is any subset of R, then A intersection E or A intersection E complement is countable at most. And therefore mu star of A is greater or equal to mu star of A intersection E or mu star of A plus 0 or mu star of A intersection A is greater than or equal to mu star of A intersection E complement plus 0, and the 0 is mu star of A intersection E complement, and this is mu star of A intersection E. So S is contained in S bar equals mu star measurable sets. Suppose E is not in S, that means both E and E complement are uncountable. So you take R equals union N in Z, N plus 1, let's say you want to take it like this. So implies there exists N plus 1 such that N intersect N plus 1 intersection E uncountable. Similarly, there exists an M such that M plus 1 intersection E complement is uncountable. Because if all these intersections were countable, then E would become countable or E complement would become countable. So since they are the same. So let A equals N plus 1 union M plus 1. Then mu star of A, this is contained in a finite interval again, which is the bigger of the two if you like, or I mean take the union and then you put them in N to M plus 1 for instance, if N is smaller, so that this is contained in a finite interval. And therefore it is an uncountable set, but it is does not have an infinite condensation point. So mu star of A equal to 1. But mu star of A intersection E equal to 1 and mu star of A intersection E complement is also equal to 1 because they all contain uncountable number of points, and therefore you have this implies that mu star of A is strictly less than mu star of A intersection E plus mu star of A intersection E complement. So implies E not mu star measurable, and therefore we have that S bar is in fact equal to S. Okay, S bar equal to S. Then the third one, mu bar on S bar is not sigma finite. So let E belong to S bar such that E bar, E complement, so E will either be countable or its complement is countable. So let us take E complement countable. I any finite interval. So if I complement intersection E is at most countable, then I complement is equal to I complement intersection E union I complement intersection E complement. E complement is countable, therefore this is countable. I complement intersection E is also countable, which is not possible. So you have a contradiction. So therefore E has E intersection I complement intersection E has to be uncountable for every finite interval E. Therefore E has an infinite condensation point, implies mu star E equals plus infinity. Therefore for example, if you take R, which is uncountable, only sets of finite mu bar measure in S bar are countables, at most countable sets. Because any infinite set which is a complement of a countable set, that will have infinite measure, and therefore R cannot be written as union EI in S bar, mu bar EI finite, because all of these will only be 0, this side will be infinity. So since mu bar of EI equals mu star of EI equal to 0 and mu bar of R equals mu star of R equals plus infinity. So you cannot have a covering, because this side is infinity, this side is 0, that's not possible by monotonicity. Okay, so with that we will conclude this section, and so next time we'll start the construction of the Lebesgue measure.